Welcome to the Copper Spice YouTube channel, and thanks for joining us. This talk will focus on generic programming and why it is not the same as metaprogramming. Generic versus metaprogramming. The original idea for this talk was to describe the difference between generic programming and metaprogramming. We thought knowing these two terms would lead to a simple explanation of template metaprogramming. There are countless websites and articles that use these terms interchangeably, which is inaccurate. Over the course of working on this presentation, we found our own understanding of these terms changed several times. This was an extremely difficult topic to research. We discovered a variety of conflicting opinions about generic programming, which create the impression that the definition can change based on the context or language people are working in. The term metaprogramming was described with various interpretations, and yet most developers only have a vague idea of what this paradigm means. This leads to confusion because we are not free to make up our own definitions of computer terminology. So why should programmers care about the differences between generic programming and metaprogramming? One reason is so you can ask if a particular language or library supports the style of programming needed to implement your application. Using generic language features is not enough to claim your application is following the generic programming paradigm. We're going to discuss what needs to be present for the code to meet the requirements of generic and metaprogramming. After looking at some definitions, we're going to show you how generics are implemented in a variety of different computer languages.
Generic programming is a paradigm where the implementation of a class or function is written using an unspecified data type. The advantage of generic programming is so the same code can be used with a variety of different types. This reduces code duplication by allowing the generic code to be reused. A generic function only needs to be written one time. However, writing the code correctly for all types can be more time-consuming. The distinction between generic programming and what we might call normal programming is when writing generic code, the type of the data is not explicitly stated. In most languages, this unknown type is represented by a type parameter like t. Generic programming is often confused with function overloading, but they have very different purposes. For example, if you want to implement a min or max function, you should use generic programming. You can write the function once and call it with a variety of data types. Each time a different set of types is used, the compiler will instantiate a unique implementation for that t. Overload resolution is the approach to use when the implementation needs to be different depending on the data type. Suppose you want to calculate the area of a geometric shape. The area of a rectangle is the width times the height, whereas the area of a circle involves pi times the square of the radius. There's no generic implementation which would make sense. Instead, you write a set of overloaded functions which have the same name and differ by their parameter list. One repeated theory we've heard is that generic programming is used to find errors at compile time. This is incorrect and misleading. All compile time errors will be found at compile time, regardless of whether the code is part of a generic function or a non-generic function. The fundamental principle of metaprogramming is to write code which has the ability to read information about some section of your program and generate code for a slightly different version of the original program. One aspect of metaprogramming is that your application can branch, potentially at compile time, to execute different code. The program is essentially doing a query of the source code to alter how the program behaves. Normally, the input of a traditional program is data with values retrieved from a database or some other input file. The input to a metaprogram is information about the source code of the current program. The output of a metaprogram is a new program which is based on some criteria. This evaluation can occur at compile time or runtime. In C++, metaprogramming can be accomplished using language constructs like if constexpr, sFine, concepts, or template specialization. For example, if constexpr will result in branching to the appropriate implementation based on some information which must be available at compile time. Concepts can be used to select the best overload based on information retrieved from the type system. An example of runtime metaprogramming would be looking at some property during program execution and then altering how the program behaves.
Generics and templates are language features which accept a data type as a parameter to a class, method, or function. Computer languages like C#, Java, Go, and Rust implement generics, while C++ uses templates. These tools are commonly used to implement generic programming. In C#, the type substitution for a generic happens at runtime. Generics in C# cannot be specialized, and defaulted types are not allowed, whereas templates in C++ can be partially and fully specialized and also defaulted. In C#, the compiler only allows the body of generic classes to use operations guaranteed by the constraints on the type parameter. This means error messages for constraint violations are more readable than the equivalent template instantiation errors in C++. In Java, the generic type is only verified at compile time. At runtime, the data type is erased and is no longer generic. For example, if the code uses list integer, this will be changed to list at runtime. The T is erased, so there is no way at runtime to know if the original type was list integer or even list string. Generics in Java do not work with primitive data types. Go is really odd, since the generic type substitution can be done at compile time or runtime. When it is done, it is dependent on the traits of T and the compiler implementation. As of version 1.18, methods cannot be generic. The generics implemented in Rust are similar to C++ templates. However, the Rust generics are currently lacking some of the power that is found in modern C++ templates. For example, Rust generics do not support sFine, but they do support traits which are similar to C++20 concepts. What is interesting is that Rust generics are used to implement generic programming. However, they are not practical for metaprogramming. If you are using Rust, macros are normally used to do metaprogramming.
Templates were added to the C++ language in 1991 with the release of version 3. It was decided templated containers should be added later as part of a library. The other problem was they wanted a generic way to access elements of a container, and the design of iterators had not been fully developed. The standard library was added to C++ with the release of C++ 98. The standard library is where template containers, iterator support, and algorithms are implemented. These language features are the basis for generic and metaprogramming, and one of the key reasons the standard library was introduced. It was not until C++ 11 with the addition of features like variadic templates and extensive support for type traits, that template metaprogramming became more common and feasible. The problem that template metaprogramming solves was based on theories which date back to the 1970s and 1980s. Template metaprogramming became popular around the year 2000, when a series of elaborate and sophisticated examples were presented, which demonstrated how templates could be used to examine or alter the current program. So what does template metaprogramming look like? The container std vector is a templated class. However, that does not automatically imply it uses template metaprogramming. We need to look at the implementation to make that determination. As we know, the elements of this container can be any data type as long as the T is movable or copyable. If you look at the implementation in Clang or GCC, the insert operation will contain code to detect if the data type is movable. This is done by calling a type trait on the T. If it is movable, the vector can choose a more efficient implementation for inserting an element. So internally, the implementation of std vector uses template metaprogramming, even though the API for the class uses generic programming. The ability for a piece of code to examine aspects of another section of code is called introspection. If the result of the introspection is used to alter or change the code of the current program, then it is reflection. An important distinction is that the code implementing reflection must be written in the same language as the program. It is possible to implement reflection in modern C++. However, it's extremely complicated, and there are limitations. Our CopperSpice libraries have a working implementation of introspection and reflection, which was accomplished using pure C++. Using a preprocessor or a code generator can emulate some of the aspects of reflection. However, these techniques are not truly reflection, since the requirement says the input and output code must be in the same language. The C++ committee has been looking at adding first-class support for reflection for over 10 years. The newest proposal is currently making its way through the committee process, and we strongly hope something will be accepted in the very near future. For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back for our next video.